reason it's not turning on. I don't know why. Yeah, that's my mistake. So it should be Wednesday, not Monday. Yeah. So the next test is next week. I don't know why. There you go. Okay. Okay, so let's get started. We were working on worksheet 16. We were talking about torque. Let's see. No, not slides. Okay. So we'll be continuing the worksheet 16. Any questions so far on worksheet 16? Number 1 and 2, we finished that. Now you guys know how to calculate torque. Torque is basically given by force times distance times the angle between the force and distance. So you want to find the torque produced by some force on an object that is fixed at some point. So this is the fixed point, which we call pivot, and you apply some force. Okay. So torque is this distance r times the perpendicular component of this force. So let's say this is theta. So this perpendicular component is f sine theta. So f sine theta. That's how you find the torque. So we'll now apply that for a condition called static equilibrium. So you should know by now what static equilibrium is, or what equilibrium is, because we already introduced the term equilibrium. So tell me what is equilibrium? Equilibrium. Literally, the meaning of equilibrium, literal meaning of equilibrium is balance. But how do you use physics to define equilibrium? We already talked about this in previous chapters. So what is equilibrium? So there are two types of equilibrium we talked last time. There is static equilibrium and dynamic equilibrium. Static equilibrium is you apply some force on an object. You apply not just a single force, but you apply a bunch of force. Let's say you apply force in this direction, force in this direction, force in this direction, force in this direction. Okay? And as a consequence of applying all the forces, the object remains at rest. Then this object is said to be in static equilibrium. Okay, so this is in static equilibrium. Likewise, if an object is moving and you apply a bunch of forces, okay, at different points, so and as a consequence of applying all these forces, the object moves at constant speed. It's moving, but at constant speed. then this object is said to be in dynamic equilibrium. We talked about that last time, just a review. Again, static equilibrium is when the object doesn't move, whereas dynamic equilibrium is where the object moves at constant speed. So for the condition of static equilibrium, we saw that the force along x direction, condition for static equilibrium. So you have a box or something, you pull this box this way. Now when you pull this box this way, the box will move to the right, it will accelerate. But to keep this box at constant, or to keep the box at rest, what do you need to do? You need to exert equal force in the opposite direction, right? So that means to keep this object at static equilibrium, the sum of the forces in x direction must be equal. Or I should say the sum of the forces in the x direction must be 0. Okay, here F1, F2 is negative, F2 is 0. Okay. So when the two forces cancel each other, it remains at equilibrium. Likewise, for the object to be in equilibrium in this y direction, the forces applied in the y direction must also be add up to 0. Okay. So let's say this is F3, F4. So you add all the forces along y direction, and if they add up to 0, then you can say that this object is in equilibrium. So those are the two conditions for equilibrium, and we already saw that in the previous chapters. Now there is a third condition for an object to be in equilibrium. So what is that third condition? Consider you have a box like this. So we said that if I apply 10 Newton on this part, this side, and 10 Newton on this side, it will be in equilibrium. But is that true all the time? If I apply the force like this, will the object still be at rest? So if I pull this, I don't know if people can see or not. So if I pull this to the right, applying 10 Newton force, and pull this, applying 10 Newton to the left, it will remain at rest. Okay, so it's in equilibrium. Now if I apply 10 Newton to that side and 10 Newton to this side, they are still opposite to each other. One is to my front, other one is to my back. But now this won't be at equilibrium. It will rotate, right? So if I apply force this way and this way, it will rotate. It won't be at equilibrium. So this force, these two forces will rotate this object. So that means it's not in equilibrium anymore. So this one produces some torque. This one also produces some torque. So for this object to be in equilibrium, the net torque, the sum of these torque needs to be 0. Only in that case, you will have the object in equilibrium. Okay. So that's the condition for complete equilibrium of an object. So we'll see some example of static equilibrium. So number 3 is an example of static equilibrium. So there's a rod or beam connected to a rope, and there is a mass hanging. So this system is in static equilibrium. It's not moving. Okay, it's not rotating or moving up, down, or front, back. It's constant. It's completely at rest. So that means for this system, all these three conditions must be satisfied. Okay. So we need to use all these three three equations that shows that the system is at equilibrium. Okay. So when we solve this kind of problem, equilibrium problem, we always draw a free body diagram, but unlike in previous free body diagrams where we denoted an object with this dot, but here we cannot denote the object with dot. So we need to draw something called extended free body diagram. So if we have a rod, so we need to denote the rod with this long square. Okay, so this replacing this dot with this kind of object is called extended free body diagram. So we'll be drawing extended free body diagram instead of just free body diagram, and then we'll need to show all the forces, okay, acting on this object. So the first part is asking to draw extended free body diagram. So for that, you can just draw the picture. So this is the wall. Okay, so you have a rod or a beam touching the wall, and this beam is supported by this rope or cable, and there is a mass hanging down the beam. Okay, and this is in static equilibrium. So the extended free body diagram is this rod, and then we show all the forces on that rod, acting on the rod. So what are the forces acting on the rod? So let's think about that. Can you guys think of forces acting on the rod? What forces are acting on the rod? Yes. So there is tension due to this cable. Yeah, there is weight. So this is T. There is weight of this. So we consider that the weight of this beam is concentrated at the center, okay, at the center of gravity, at this center. So all the weight is concentrated at the center, so that's the weight of the rod or beam, let's call that WB. And also there is this mass hanging, that means it's pulling this rod down, so there is this weight of hanging mass. And what else? There is also friction. This rod tends to move down, okay, it tends to slide down if there were no friction, but because of friction in this upward direction, static friction, it remains at its place. Okay, so there is this friction, and since this is resting on this wall, that means the wall provides normal force. Okay, normal force. So imagine that there is no normal force. What will happen if there were no wall? The beam will just move to the right. But because of this wall's normal force, it remains at its place. Okay. Likewise, if there were no friction, what will happen? This will just slide down. But because of the friction, it remains at its place. Okay. So these are all the forces that are acting on the beam. Friction, normal force, its own weight, weight of this hanging mass, and this tension. Okay. So this diagram is called extended free body diagram. So that's the answer for part A. And the next thing is, it's asking, write Newton's second law along x-axis. So what is the Newton's second law? So Newton's second law is sum of all the forces is equal to ma x. So what are the forces along x direction? We need to write all the forces along x direction. So we choose this to be positive x, this to be negative x, this to be positive y, this down to be negative y. So focus only on the forces that are along this x-axis. Yes, no, normal force is, yes, yeah, normal force. Is it positive or negative? Negative. So normal force, and what else? Yeah, so this tension is in between x and y axis. So if you consider this to be y axis, you have this x axis. So let's consider this to be theta. Then it's plus t cosine theta. Okay, so those are the two forces along x direction, and that would be 0. Okay, because there is no acceleration. The block, the beam is not moving to the left or right, so it's at rest. No acceleration. Okay, so that's 0. Likewise, write the Newton's law along y direction. So write all the forces that are on y-axis, along y-axis. So the first one is y component of the tension, which is t sine theta, and it's positive because it's pointing up. There is this weight of this hanging mass, which is pointing down, so it's negative. There is this weight of the beam, W sub B, and there is this friction, which is positive, and then sum of all these would be 0, because again there is no acceleration in y direction. Okay, so that's answer for C, B and C. Now write Newton's second law for all the torques. So just like the Newton's law for linear motion, we can also write Newton's law for rotational motion, a rotational part. So in the rotational part, Newton's law is, it becomes, instead of force we have tension, torque is equal to, we haven't talked about that yet, but for this case we'll just say 0. Okay, sum of all the torques will be 0, because this object, in the next chapter we'll be talking about how to replace mass and acceleration in rotational part. But for now, let's just say that there is no rotation of this object in clockwise or counterclockwise. Okay, so no rotation. So if there is no rotation, that means all the torques should be equal to 0. Okay, that's the second law. So Newton's second law for rotational motion. So this means there is no rotation. So we need to add all the torques from this picture, from this diagram. All these forces tend to produce torque, and those torques should be equal to 0. That's the condition for no rotation. So you guys tell me all the torques we have. So where should I write that? Let's see. Let me just erase that. Okay. So to find torque, we first need to define a pivot or a fixed point. Okay. So choose a fixed point about which the object tends to rotate. Now, since this object is not rotating, that means you can choose any point as a fixed point. Okay. So since it's in equilibrium, meaning it's not rotating, so you may choose any point as pivot. Okay. Pivot means point about which it rotates. Okay. So which point should we choose as pivot? So usually we would choose the pivot about the point which has unknown force. I will show you example of this. Okay. So some of the forces may not be known. So here you may be given tension in the question, you may be given the weight, you may be given the weight of this beam, you may be given the angle, but you may not have friction, you may not have normal force. In that case, so the friction and normal force are acting at this point. So we will choose this point as our pivot. Okay. If, for example, friction and normal are not known, then this point will be our pivot point. So you can choose any point, it doesn't matter. So just choose this point as the pivot point. Okay. Then let's now, for each of these forces, find the torque. So torque due to tension plus torque due to all these forces tend to produce torque due to WB plus torque. You don't need to write all these words. I'm just writing to make it more clear here. So torque due to normal plus torque due to friction. So these all torque should be equal to 0. Okay? And the reason for that is, again, this is in equilibrium, it's not rotating. So now let's find the torque. So what's the torque due to the tension? Formula for torque. Formula for torque is distance at which you apply the force, distance between the point of application of force and pivot, this distance. Okay, so this is our pivot. And here we are applying the tension. So we need to consider this distance, which is the length of the rod. Okay, this is the formula for torque. So torque produced by tension is distance between the force and the pivot times the force, which in this case is tension, and sine of angle between the distance and the tension. So that's the torque produced by tension. And we also need to think about whether it is positive or negative. Do you guys remember when is a torque positive and when it is negative? Yes, so someone has answered here, Travis. Clockwise is negative, counterclockwise is positive. That's good. So think about, if this is a fixed point, if you pull this rod along this line, does that force tend to rotate the rod clockwise or counterclockwise? Clockwise, exactly. So this would be negative if it is clockwise. Okay. This is the torque produced by tension. Okay. Now torque produced by the hanging weight. Okay. Let's not put the sign yet. So this one, what's the distance between this point and this point? Is it given? It's not given, but we can just consider that distance to be LH. Okay, so distance between the point where we apply the force and the pivot. Okay, that's that. And then the force. So force here is WH, and angle between the force and the distance. What's that angle? So this is the rod. This is the weight. That's our distance. So what's the angle between this weight and this distance? 90 degrees. Yes, so that's 90 degrees. Now, does it produce the rotation in clockwise or counterclockwise if this is a fixed point? Counterclockwise, yeah. Oh, wait, no, it will rotate like this. Yeah, it's counterclockwise, so that means it's positive. Okay, so that's the torque produced by WH. Now, torque produced by WB. Okay, so tell me, what's the torque produced by WB? First thing is distance between the point where you apply the force and pivot, this distance. What's that distance? It's half of L, right? This whole thing is L, and that's half of L. And what's the force? Force here is WB. And what's the angle between this distance and the force? It's again 90 degrees. So sine 90 degrees. Is it positive or negative? It's positive because it's counterclockwise. Plus torque due to N. If the force is at the pivot, then you don't even have to calculate that. You can just directly say 0 and 0. Do you know why? Because the distance is 0, right? The distance between the point where you apply the force and pivot is 0. So this R is distance between force and pivot, which is 0 in this case because both are at the same point. So that's why it's 0. Same thing with friction. So friction is applied at that point and pivot is also at that point, so that's 0. Okay, so that's Newton's second law for rotational motion, okay, which is the answer for D. And because these things are 0, we don't need to deal with friction force and normal force. That's the reason we are considering the pivot at the point where we have unknown forces. If we do that, see, that makes it 0 and you don't have to worry about those forces. Now let's look at some of the problems, and that will make the things more clear. since you are looking this kind of problem for the first time, so it may be a little bit confusing, but now if we look at a problem, that will make the things more clear. So let's look at number 2, or no, sorry, not number 2, number 4. So there is a ladder resting on a wall. So just draw this picture. So there is a wall, and this is the floor. Okay. So there is a ladder. Okay, so that's ladder. And the ladder is in equilibrium, static equilibrium. That means it doesn't move to left, right, up, down, or it doesn't rotate. So it's just at rest. Okay. Since the ladder is at rest, so that means it must satisfy those 3 conditions. So for any object to be in equilibrium or static equilibrium, the condition is, or the conditions are, first one is sum of all the forces along x needs to be 0, sum of all the forces along y needs to be 0, and sum of the torque produced on the object would be 0. There shouldn't be any, this means there shouldn't be any rotation, there shouldn't be any motion in y direction, there shouldn't be any motion in x direction. In that case, this would be perfectly at rest. Okay. So the length of the ladder is L, and the ladder is resting on the wall at angle theta to the surface. So what was the question? Question is draw extended free body diagram. So let's draw extended free body diagram. So the mass of the ladder, or the weight of the ladder, is concentrated at the center. Okay? If this is the center, then its weight is concentrated at that center. So the weight would be pointing down. So this is the weight of the ladder. If it is a uniform ladder, then its weight must be at the center. Oh, there is a person. Okay, so there is also a person standing at 2/3 way up the ladder. Okay, so this is halfway. So 2/3 is somewhere here. So there is a person standing here at 2/3 L. So that means there is weight of this person also pointing down. So that's WP. What other force you can think of? Yes, exactly. So there is normal force. Imagine that there is no wall. In that case, this will just move to the right. So because of the normal force of the wall, this one doesn't move to the right. It's just resting at its place. So there is normal force of the wall. What else? Hmm? No, normal force of the person. There is a normal force on the person, but we don't need to worry about that. We only care about the ladder. We are only looking at the force on the ladder, not on the person or on the wall. What forces are acting on the ladder? Sorry?
Normal force of the ground.
Yes, so there is a normal force. If there were no ground, then it would just move down. But because of this ground, it's providing this normal force, so that means it doesn't collapse. So there's n, let's say, floor, okay, n floor. And if there were no friction, then this ladder would slip, okay, it will just move this way. But because of the static friction this way, it doesn't slip. Okay, so there's static friction. And it says that there is no friction on the wall. There's no friction on the wall. So we don't need to worry about the friction on the wall. So friction is 0 for the wall. Here, there's friction that prevents it from slipping. So those are the forces we have, okay? Now we need to write these three equations for those forces. So the first one, add all the forces along x direction. So let's consider this to be our x direction and that to be our y direction. So what are the forces along x direction? We have this friction force. It's positive, it's pointing to the right. There is this normal force which is pointing to the left. So NW. And what else? Yeah, those are the only forces along x direction. Okay. Let's call that equation 1. Now, apply this one. Sum of all the forces along y direction. What are the forces along y direction? There are a bunch. So we have NF, normal due to the floor, positive. There's weight of the ladder, pointing down, weight of the person, and then, what's that? Yeah, those are the only forces we have. We don't have other forces. That's 0. Right? So we considered Fs, that's gone. We consider that's gone. So we have that NF, we have WL, we have WP. Yeah, those are the forces. We have 5 forces. They are all in these two equations. Now, the third one. So we need to add all the torques produced by these forces. So for torque, because torque produces rotation, we need to first decide a fixed point about which the object tends to rotate. Although the object is not rotating, but we can choose a point where it tends to rotate. So it's up to you which point you want to choose as the pivot or the point about which it tends to rotate. You can choose, you can choose bottom or top. But why you want to choose bottom? That's right thing to do. Because if you choose the bottom, you have 2 forces, then you don't have to deal with these 2 forces. If you choose top, then you only get rid of 1 force. Right? So it's better not to deal with like 2 forces than to deal with 1 force. So it saves our work if we choose the bottom one, and then we don't have to deal with the 2 forces. So you can also choose this one to be your pivot or this one to be your pivot. Whichever point you want, you can choose as pivot. But let's choose that as pivot. So now, starting from top, think about all the torques produced by the forces. So the torque produced by this force, again, torque is Rf sine theta. That's the formula for torque. So what's the distance between this force and the pivot? L, yes. So L, and what is the force? Force is NW. Sine, what's the angle between NW and this distance? So this angle and this angle are same because they are alternate angles. So yeah, 30 degrees. So sine 30 degrees. Now, so that's done. Now, also think about, if this is our fixed point, will the rotation be counterclockwise or clockwise? Maybe counterclockwise, yeah. So that would be plus. Now the next force is this weight. So to find the torque produced by this weight, first think about this distance between this force and the pivot, which is 2/3 L. So distance is 2/3 L, and our force is WP. Sine, what's the angle between the L and W? This angle. This angle is angle between R and F. What's that distance? Sorry? Wait, it's not 90. It's 60, yeah. So this is 30. If you draw a triangle here, this is 90. So 30, 60, and 90 would be 180 degrees. So this should be 60 degrees. So sine 60 degrees. And is it clockwise or counterclockwise? So this is fixed point. It's clockwise, so that would be negative. Next force is this one. Distance between the pivot and the force is halfway the ladder, that means L over 2. Force is WL. And then sine, what's that angle between distance and this distance and force? It's 60 degrees again. So sine 60 degrees. And then these two won't produce any torque because distance between R, or distance between the force and the pivot is 0. So that's 0. And that should be 0. Okay? So this is third equation. So it's asking what's the minimum static friction which will keep the ladder from slipping. So we want to find yes. Oh yeah, sorry. So this one would be negative, yeah. So we have those three equations. So we want to find mu s. So how do we find mu s? Any idea?
It's the coefficient of static friction.
So coefficient of static friction is related to this mu Fs. Fs is mu s times n, right? So if we could find that, then we can find mu s. So we need to play with these three equations.
Are we going to need to find n? Is that an f in this instance?
Sorry, what's that?
Would the n there be an f of the normal force of the floor in this instance? Instead of the
Because
we have two normal forces.
Oh,
For equation 1 and 2, or which one are we going to use for N and W or NN?
you can use either one. So this is F.
In our formula for static friction, in this diagram.
Okay. I see. Okay, okay. So here, friction Fs is this one. So that means we need to use NF here, floor, because we are dealing with the floor. So that means that should be that of the floor. Okay. So how do we solve the equations? That's the main thing. That's the hardest part. Up to here, it's not that difficult. Solving equation is the hardest one. So here we want to find, so you can write mu s n for the friction, and that will be equal to nw, right? So you can take this to the right, so that becomes that. So Fs is that, nw. So then mu s is equal to nw over nf. So you need normal of the wall over normal of the floor to find the mu s. So normal of the floor you can find from this equation. So let's first find that. So let's do that. Let's do this one at a time. So use equation 2 to find NF. So use 2 to find NF. So NF is equal to WL minus WP. W is mass times G. Is weight given? Oh, weight is given, so we don't need to worry about this formula. We can just directly use that. Okay, so weight of the ladder is given 150 Newton. Weight of the person 300 Newton. Just a second, did I use this formula? Oh, it should be plus. So when you take these to the right, both of these become plus. So that's plus. Okay, so adding these two, you get 450 Newton. So that's what we got. Now we still need to find NW. For NW, we can use the third equation. I know it's a little bit lengthy. You may be a little bit lost on that, but with more practice, I think that'll be better. So use third one to find NW. Okay. So this is what we want to find. So plug in all the numbers. L, length of the ladder, 5 meter. I will not put the units, so I'll just use the numbers. NW sine 30 minus 2/3 L is 5 meter. Weight of the person is 300 Newton. WP weight of 200, and sine 60 minus length of the ladder 5 over 2. Weight of the ladder is 150. Sine 60 is equal to 0. So everything here is known except NW. So you find NW. So we found NW as well as NF. With that, you can find that. So let's find NW. Why don't you guys find NW? See what you get. Okay, we have a minute left, so let's see if I can finish this in a minute. So 5 NW sine 30 degrees minus I don't have calculator, so let's see. Don't have answer for that. Okay, yeah. Well, I think we'll finish this on Friday. So why don't you guys try that at your home, and then maybe on Friday you guys can tell me your answers. Okay. So that's all for this class. We'll do some more practice next time.